Okay, so sorry, a little delay. I want to finish up the discussion of GNNs today and start into RNN related topics, which is the next big topic for the class. I mean, it's not that big. We're going to spend maybe a lecture and a little tiny bit on it before we switch over into talking about attention and transformer models. They're very important practically these days. Before I start on this, I just wanted to remind people, we do have the midterm coming. So again, midterm is Tuesday, March 21st, 7 to 9 p.m. That's the week right before spring break. As a result of that exam, so people have asked a little bit about the scope of the exam. The scope of the exam is everything up through the homework that you've done that was due that weekend. So what we're going to do is so the discussion and lecture before also counts, but the lecture immediately before the Monday lecture is going to be, not really in scope because the exam's the next day. We're going to do a couple of things for the midterm, telling you guys in advance that on that Tuesday, the discussion sections will be oriented towards a last-minute review. In case people have any questions, we'll try to arrange them by topic so that you can choose which one to go to based on which topics you would like to get a little bit of extra review on. The week of the midterm, so people have asked, what is the status of spring break for the course? We're going to treat spring break like it doesn't exist, meaning that it's just a period that exists outside of time. Okay, so there will be no homework assigned that is going to be assigned, during in spring break and things like this. It'll just be as though it didn't exist. Is the status we're going to use. So what we're going to do is that week of the midterm, we're going to go a little bit lighter on the homework for you all. So the main homework that week is just going to be you get to do the midterm again, and we'll give you like maybe one other problem or something. And that will be due kind of with spring break in the middle. The grace period of normal 24 hours will actually extend over the entire break for that particular week. I want to say that next week, we're going to start releasing project details. So you'll get a chance to, we'll have kind of an approach for you to start on the project, start assembling teams and the like. The project is going to have required teams of 4 people. We'll announce all the details of that next week. So once the project is fully underway, the homeworks will get a little bit lighter in time so that you have more time to spend on your project. But we expect the overall workload in the class to kind of stay constant or ramp up a bit, actually, because of the project for everyone. Okay, good. That's like administrative announcements. So back to graph neural nets. So at the very end of last lecture, I was a little bit compressed for time, and you're already seeing it in the homework. But I just want to make sure that everyone understands it. We talked about how we can go from graph level tasks to node level. Node level tasks. So I want to make sure that everyone gets a chance to ask questions to make sure you understand what's going on here. And so there's a couple of different reasons that one thinks about this. First is that you already saw in, as I mentioned, in CNNs, that when we talked about the UNet, that there are going to be tasks on images that are pixel level. So the counterpart here is going to be node level. The other thing is that there are many graph algorithms that you already know, that you've seen, that already are working at the node level. So lots of interesting questions exist at the node level in graphs. So these are interesting problems, so we need to see if we can use GNNs to deal with them. And the other is actually, if you think about it, comes from stepping back a bit. It says that when we talked about a graph neural net, what we did was we had weight sharing that was kind of being operated across the graph. So, and we didn't care necessarily about, whether there was diversity in terms of the number of connections and things like that through the graph. So from that perspective, the fact that you have weight sharing across different nodes in the graph anyway in your architecture tells you that as a technical matter, you can support node level tasks, right? Because you could imagine holding out some nodes. So that's like the interesting kind of, it's good for you to be able to reason both ways, right? From the problem side, that there's definitely organic problems that occur. From analogy, saying that we saw something in this domain, what's the analogous thing here? See if you can complete analogies. And also from just looking at the technical capabilities of what you have, right? In a convnet, it's very hard to think about holding out pixels, right? It's a very strange thing to do. You can kind of, if you think about it now, you can think, yeah, I could do that. I could zero pad them or something, right? But in a graph neural net, it's very natural, the idea you could hold out nodes. Okay, so all these kind of tell you can do node level tasks. So it's like a slower commentary on this. I wanted to make sure that you all got. So what does this mean? Holding out nodes. So when I say holding out nodes in the graph, we can think of it as you either have actual labels on the entire graph for every node, or you have a graph that has lots of nodes in it, some of which are labeled, and some of those labeled nodes you want to hold back as a validation set. Right? Both are encompassed by this. So for holding out nodes, we have two general approaches that we can follow. Kind of spiritually. One is simply deleting the held out nodes and all associated edges. During training. You pretend they're not there at all. That's the approach that we tell you to do, I think, in the homework for the coding question. And what that does is it says, okay, they're just as though they're not there in the graph. You learn weights for your graph neural net that tell you how to aggregate information, how to process it, and so on. You get gradients during training from the labeled nodes. And that's that. The other choice is used when that simple deletion of the held out nodes would kind of very substantively damage the topology of the graph and wouldn't let you have connect things up. So the other thing is keeping the nodes and graph and associated edges but removing the information. In the node. So this can be tricky. This is really relevant for cases where you have nodes that have labels on them, that have information, like some vector associative information. And they also have a label associated. So keeping the nodes that you want to hold out, they have a label associated with them. So when you talk about removing the information in the node, this definitely means, so when you completely remove it, this is obviously not showing up in the loss. either, so it's not there at all. So this also includes, not in the loss for training. For sure, right? And also typically involves some kind of removal. So here I'm going to put it in quotes, because by removing it from the training loss means that's an easy way of simply deleting the label information, because the label information on a node only appears during training, right? The same way if you think about the, semantic segmentation problem where you have a pixel label, right? That pixel label only shows up during training, as causing in the loss function causing a gradient. So that's easy enough. But what about the information that is in the vector, right? The vector label on the node itself. What do you do about that? So you want to remove it. But how do you remove it? So for the removal of the node label, there's many choices of what you can do. One thing you can do is to simply, for example, you can do this by replacing with a 0 vector, right? If 0 isn't particularly meaningful, you can just use 0. But if 0 is actually a meaningful label, right, then this is not good, because now you've actually put something meaningful in there, and you don't want to do that. So you can also do with, sometimes it's called like mask, a special label that means like nothing here. How you do this is sometimes domain specific, and often involves pre-processing a little bit before you put information into the graph neural net. So you embed the actual node labels into something larger, and in that larger space you stick in a new vector somewhere that's like no information here. It means no information here. So when you do this approach where you keep the node but remove the associated information, this allows messages to pass over that node using message passing language. Thinking about it in terms of the graph neural net topology, it means that the graph neural net has nodes associated with these removed nodes that are participating in later stages of processing. Just they have nothing interesting to say at the beginning. Okay, but they're not in the loss. So any questions on this? I want to make sure everyone understands this idea. Any questions? No? Yeah. Yeah, so if you think of your graph neural net as involving some kind of processing that you're doing, right, to the vector input. So the vector inputs come in, the first layer of your graph neural net. First thing they encounter is some kind of MLP, right? So they'll see this MLP, and then they'll get some nonlinearity. In that MLP, they'll get processed in some way, and then they'll be sent off as messages to everybody else, right? Kind of in terms of processing, right? That's the first thing that happens. So you want to remove it, but you want it to participate in taking information from its neighbors. Okay? So if you need it to take information from its neighbors, but have no information itself, you have to convey that somehow to the graph neural net. But the problem is that when you write stuff down in like math, you can just add another symbol, right, called like erasure or nothing here. Right? You can augment your alphabet. Say, okay, instead of the input being the set of the vectors from Rn, we're going to have Rn union special symbol. right? So that's easy enough to write. And in code, you could also imagine using some appropriate data structure augmented that has a special symbol and having it, participate in operations in some way. But that becomes trickier, right? Because the processing of the graph neural net is like all based on these real vectors. So you can't necessarily have this special symbol. That's a special symbol. But you want a special symbol. So now you're in this situation. You want something. You cannot implement it in the straightforward way. So what do you do? Does everyone understand? Like, this is like important. It's a good question. So what you do is you have to put something there that's not going to show up naturally in the data, because it should be different. So you need it to be different. So how do you get something different? So one way to get it to be different, for example, the easiest way, right, is you could say, well, I'll take my original data is vectors of length 3, right? And I'll embed them into vectors of length 4. This is one approach you can think of. Where if this is valid information, we'll put 1 here. I'll give you an example, right, of something you could think of. And if it's not valid information, we'll put a 0 here. That's a way of generating something which is like a mask. It says don't, and it should learn to ignore this. Okay, here's the thing. What saves you here is that you're going to train the neural net, right? And so you want it to learn to ignore this information. Right? There's no choice. There's no way of like forcing it to ignore it by arithmetic itself, because you can't put an if-then in ignore. And even what does it mean to ignore? Because you have a combining rule or a similarity rule. Like, how do you do that? So you need to learn to do it. So to learn to do it, which is great, it has to learn to do it, but it also means it gives you some flexibility. As long as it's clearly distinguishable, you can do it. So if you put a number here. Now, this is, of course, a very simplistic approach. If you want to give it ample opportunities to learn, and you're not that worried, you could simply take this data and instead embed it into an even larger space and just throw another vector in some random direction out. Right? So you have everything, the interesting data is in one subspace, right? And then a mask is somewhere else. Because then you know, okay, good, I know the kind of operations I'm going to be doing. I'm doing projections and stuff like this. So it'll be able to figure that out, that something's in a different subspace. You see what I'm saying? So that's what I mean by mask. So later on, we talk about, so this mask idea that comes up very naturally in the context of holding out for graph neural nets turns out to be really important later when we'll talk about like self-supervision and pre-training of these models like BERT and things like that, where you also need to basically delete some information. So the same idea is used. Yeah.
Could we just, for the nodes that are being held back, remove the its own vector for those nodes and just have a different up?
Okay, great. That's a great question. So the question was, could you instead do surgery on the node's graph, on the operation that it does, in which you say, remove the dependence on self? Okay? So that's an interesting idea. But the problem is you have to do weight sharing. You want to do weight sharing across the different nodes in the graph. So your function might not have a good way of removing dependence on self. So it depends on the structure of the update function. If the update function is something which is some function of self plus some function of neighbors, then you could imagine replacing self by some kind of average or something that's like not informative proxy. And then you can still do weight sharing on the weights on the functions that depend on others. Right? That's fine if that's the structure of the function, like a plus. But that we mentioned that's not always the kind of thing you would do, right? You might do something which is has a more interesting dependence on the others. For example, looking at the similarity between me and them, and then weighting things appropriately. In that case, it's hard to remove the dependence on self in a weight sharing way, in a kind of just by explicit surgery. I know I can do this. So then you just count on it to basically learn that somehow. Good question. Okay, great. So these are like, once you have this, once you have these ideas, then everything else follows kind of just organically. You can just think it out. You want things to work, what do you have to do? And everything just, you know, ask you to do the homework, you should be able to figure it out from the spirit of what's happening. The interesting thing is, because you can do holding out of nodes, it allows the possibility, as I mentioned before, of doing graph neural nets and training them on a single graph, right? Instead of having to have many, many graphs. You can have a single graph and you can train on that one graph. You still need enough data, but the enoughness of the data might come from the number of nodes and edges in the graph. So that's also interesting. And it should make you think. In the graph context, it's natural, but it should make you think about whether or not it's possible to do interesting training and interesting like adaptation using the kind of tools that you've learned on a single image. Okay, do you guys see that? If you have one big image, if you know that for one big graph you can do training on the graph, it suggests that you should be able to do training and some kind of learning with one image. Any questions on that? Just as a, you understand? I'm not saying you should understand exactly how to do that, but you should understand why that's an interesting question to think about. Yeah. So in the homework, we give you a pretty small graph, right? And it kind of works on that very small graph. So the answer is, it doesn't have to be that big, depending on the, so in general, the rule is the amount of data you need should be commensurate larger than the sort of complexity of the function you're trying to learn, right? So that same thing applies here. So in the homework, we give you a very simple little graph from a paper and about this karate club, and we're trying to figure out like which faction people belong to, and it's a pretty simple kind of clustering style problem, and you can learn it. Other more interesting functions that people care about, for example, if you think about Netflix, Netflix has a problem. I'm not sure if Netflix uses graph neural nets, so I'm just using it as an example, where you have a graph of many, many thousands of items of content and many, many millions or hundreds of millions of users, and you want to learn from this. So, and presumably the things they want to learn are much more interesting than just a cluster. But you have a large graph. But you should think about it from the context of images for yourself. When you look at a connet by itself, just if all you learned was a connet and thinking about training a connet, the idea of being able to train a neural net on one image is not going to be natural at all. It'll just feel weird. Completely, you won't even think of it. But that's one of the reasons why you have to learn these different things, because natural questions in one can spawn analogous questions in the other. You need to go back and forth. Okay? Any other questions related to graph neural nets? We gave a very brief kind of survey of this topic. We pointed you to a blog post. If you read it, which I strongly encourage, you should see how there's like a much, much more, many, many more things that are actually interesting that you can think about in the context of graph neural nets. And we haven't touched at all, really, on the implementation challenges in very big things. because we can't give you homework on that. We don't know how to do that. Okay, good. So with that, I'm going to stop talking about graph neural nets, and I'm going to start talking about RNNs. But I'm going to do this pivot in two different ways, right? The main way I'm going to do it is, again, I'll go from ConvNet to RNN. But I wanted to also move from graph neural nets to RNN by pointing out something interesting that we saw in graph neural nets. In graph neural nets, you saw that because you have the basis of graph algorithms, on graph, you saw that it can be interesting and natural to want to do the same operation over and over and over again, right? Because if you think about, I think in discussion you talked about like shortest path, right? You think about just computing all pairs shortest path, you basically are taking mins over and over and over again, right? And so the idea that different conceptual layers of processing might actually share weights among them is something that wasn't natural in the context of a convnet necessarily, but is a natural thing to think about in a graph neural net. Okay? So one way to think about RNNs is to ask the question, where else could that be natural? So that's one way of doing it. But the way that I'm going to talk about it is actually, I'm going to take a signal processing based perspective. Okay, this pen is dead. So the SP perspective I'm going to use is going to be that in a convnet, we had filters defined by finite convolutions. Okay? Right? That's what we had. We had little 3x3s or 7x7s or whatever filter blocks that we learned. And so the SP analogy is FIR filters. FIR stands for finite impulse response. So again, remember, deep learning is a younger research area. And all younger research areas, well, all research areas, but especially younger research areas, usually benefit a great deal from what you might have heard of called intellectual arbitrage. So has anyone heard the term intellectual arbitrage? Raise your hand if you've heard this term. Okay, a couple of people only, so I'll describe it. Who's heard the term arbitrage? Few, right? So arbitrage is basically you buy something cheaply here and you sell it over here at a higher price, right? And you make money this way. So intellectual arbitrage is the same principle applied to ideas. You take an idea that is well worn and established here, right? So that you can buy it cheap, and you bring it over here and you innovate by bringing over an idea. A lot of the advances in science and engineering are grounded in intellectual arbitrage. So you take ideas from here, bring them over here, and use them. Younger fields, especially, benefit a lot from bringing ideas from neighboring areas in and using them. So because we know there is a very fundamental connection between signal processing and deep learning, since deep learning is learned signal processing, you should always ask the question, is there an analogous family of things in signal processing that might have been studied? So in the context of FIR filters, of course, there is. So there exist infinite impulse response filters. Spelling is weird. And so the question becomes, what is the counterpart here? Like, what's the, in question net, we have filters, these are learned, right? Something. You see how we're doing this? Right. Any idea that you can connect, you say, over here, is there a family of ideas? Who else is here? And then bring it over. Okay? So you ask yourself, okay, let's think about infinite impulse response filters. What are these? So again, if people haven't seen IIR filters, they're not particularly complicated. So the basic idea is I want to have, so in SP, I want to have a convolution that's infinitely long, right? How can I possibly have a convolution that's infinitely long? Well, I have to be able to, and use it in practice. I have to have a finite description of that infinitely long thing, right? You can't actually do any truly infinitely complex operation on a computer, right, or build it. It has to have a finite compact description. So in IR filters, what you do is you instead, you get infinite response length through the use of filter state. Okay, you have filter state in your filter. So what's an example? We've already seen this when we talked about momentum, right? So the example is you say, okay, I have a filter where the output at time, I shouldn't use, I'll use subscripts. Output at time t+1 is some number times yt plus some other number, beta 1, beta 2, times some input, ut. This is a linear filter, right? It takes inputs u, a sequence of them, and it maps them to a sequence of y's in a linear way. Okay, so you remember this from momentum, right? It's a way of doing averaging with a compact representation using state. So that's what an RNN is. It follows the same like completing this analogy. Okay, so you have internal state. So one thing you know about FIR filters is, they're defined by some kind of sum of the impulse response, h of e minus I from something to something else, input u of I, right? They're like a moving average. And in an infinite impulse, in a finite impulse response, you didn't care whether you had negative numbers here or here. or positive numbers. It didn't matter. It's just an average of nearby things. You could look backward or forward, it makes no difference in the understanding of it. But when you think about state, state definitely has this direction of time and evolution in infinite impulse response filters. So you need to have a direction of time here. So these constants apply to anything that you can put down. You can put it on a, any way you want. RNNs in their native form depend on sequences, right? Native to sequential data. One thing after another, sequences. Okay, so I will pause here first to make sure that people understand the analogy I'm making, and then we'll flesh it out. Okay, and the way we're going to flesh it out is we're going to first do an example of something that many of you might have seen, and we'll kind of think about it as a modeling tool, and then we will extend it to RNNs. Okay, following the general philosophy that if you think about what happens in neural nets, you can think of what happens in neural nets, at least for convnets and MLPs and RNNs, as being, let's understand what happens, a natural set of operations in the linear world, and then let's make a nonlinear version of that that's learnable. Okay? That's how we've understood everything. So we will do that same program for RNNs. So we'll start with a linear example. Okay, so questions on this? Maybe I'll just get a sense of the people here. How many of you have seen finite impulse response filters and infinite impulse response filters in a previous course? Okay, very few. Okay. Probably should know this stuff if you're going to be working in this area, because it's a rich domain of intellectual arbitrage. So you're missing out if you don't know it. Yeah.
Are we saying that convnets are like FIR and RNNs IIR?
Yep. Because the convnet we're defined by finite convolutions followed by nonlinearity. Finite convolutions are FIR filters. So we're saying, what if you wanted to use a sequence of filters to process data where those filters aren't FIR filters, but are instead IIR filters? All done all the time in signal processing. So what would that mean? So we have to understand, okay, well, I know exactly what that means for signal processing. I have a filter defined by internal state. And I can put them one after the other. That's all fine too. So the question becomes, okay, what is the learned version of that? And then what is the version of that that I can introduce a nonlinearity to gain more expressive power? If I do that, I will get myself to RNNs. But I have to remember the key limitation is that FIR let me use it anywhere I could basically define a local neighborhood, which is what this is. See that? This is like a local neighborhood, which allowed us to have the generalization to graph neural nets easily with local neighborhoods. For IIR, I have to have sequential processing. I have to have internal state, and I have to let that state evolve. State has to evolve in a direction, as natively understood. So I need to think about sequential data. That's the story. Okay? This is how do you discover RNNs, as opposed to here is in the great book of deep learning RNNs. It's very important you should learn things from the perspective how do you discover it, because you'll be reading papers where new stuff will come up all the time. And you need to be able to do that yourself too. Okay? Any other questions on this basic analogy? What's going on? Do you see how this is like a linear function, right, of the sequence U? We talked about already in momentum. Yeah. Yeah, it's a really great question. The question is there are there analogies in deep learning to the difference between open loop and closed loop control? And the answer is yes, there are. Those are still being built out, though. They're less fully mature. Most of hard to say exactly. You can conceptualize certain kinds of RNN-style architectures using understandings of closed-loop control. But it's not as well developed. Where it really comes up, where those analogies are very important and useful, is actually when we start talking about things like diffusion models and generative models like that. There, literally, control type ideas are very important to what happens. So that's where that connection is really being fleshed out more. Good, great question. Okay, if this is very clear, so you understand what we're trying to do, let's do it using an example. Let's understand an example. So for an example, I'm going to pick something that's basically, again, I think some of you have seen this and some of you have not, and that's fine. It's going to be self-contained. But we're going to take an example, probably the most famous example of kind of the use of filters in practical problems. And the most practical example of filters in terms of real-world deployments of the infinite impulse response type, which is filters that have internal state, are common filters. Common filter inspired example. So again, I'll take a brief poll. How many people have seen or heard the term common filter? Yeah, a lot of people, right? It's very... So a common filter, basically the classic, so think about the classical treatment of a common filter. So classical approach. Classical approach is you have some system have a true system which you have a description of. So you know exactly how it operates. And in this true system, I'm going to use slightly RNN-inspired notation. You have some state, ht, is a vector, which is there's some a true that is the way that ht plus 1 depends on ht. There's some b, which is meeting some driving white noise or something that's driving it. And you observe a sequence xt, which is some c times ht plus, I don't know, some other noise, vt. So has people seen it this way? I want to make sure I match the kind of style that people have seen. So some true thing that's going on where you have some linear evolution of some state. And you only get to observe kind of noisy observations of it in some way. And what you want to do is to build an estimator that will take these observations and give you an estimate of the true state. But this is the classic treatment of a common filter. So you're given this. You want an estimator which you can run, which is some h hat t plus 1 is going to be some other matrix, right? Potentially a prime times h hat of t, so it's going to depend on the past thing you had for the estimator, and you're going to take in the observation you have, some b prime xt. Okay? Now, in the classical stuff that you've seen in your classes, what you do is you say, okay, I'm going to make Gaussian assumptions on what's happening here. Then I'm going to compute the explicit Bayes rule estimator, which will give me the map or MMSE estimate for the state. I will then compute the update for that state, and I will get an equation like this. And in fact, what you actually know about Kalman filters is pretty sophisticated. If you've seen them, is that actually you can deal with known time variation in these things, and you can have it initialize at places that you know are wrong. You can have these things also be time varying. You know a lot if you studied Kalman filters, and if you for example, every mechie who has to do anything knows how you need to make extended Kalman filters, and you do lots of stuff that you know, right? If you've used Kalman filters, but all of it is predicated on the idea that you have this true system in your hand, and then you have formulas that go from here to here. Okay? So does everyone, that's a classical Kalman filter. There's a hidden state, you want to estimate it, and you can do it. Great. Now, I'm going to talk about what we want. This is the classical. So we want a learned filter to do this job. Okay? Standard thing, right? Now, instead of saying that we know the dynamics of the true thing, like when we have a learned filter, we say, hey, I don't know any of this. All I know is I want an answer that looks like this. But I don't know what these weights are, right? So if you do this, we treat A prime and B prime as learnable weights. So we have to learn it from data. Okay? Now the question is, what does our data look like? Okay? What does our data look like? So if you start with this problem, you say, I want to learn from data, and I want to think of what kind of data. Let's start with the easiest case. Okay? The easiest case. So the easiest case is we have sequences of trajectories of the true system. Okay? Okay? Underline the S, plural. Okay? Potentially, right? So we have sequences of measured trajectories. With ground truth. Okay, so what does that mean? It means I have actual HT, observed XT, and I have this comma j for the jth trajectory. J equals 1 to nj or something. So I have these kind of trajectories that then go across time for however much time you have for every single one. This is for, sorry, this is, let me make it more precise. T equals 0 to nj. And you have these sequences for j equals 1, I don't know, m, some number of them. Does everyone understand what we're doing here? Okay, so we have all of this. So now the question is, here's the exercise. We could give this to you as a problem. I think we'll kind of have a little bit of this in discussion, but I want to make sure you understand it, because we really want to make sure you understand it, is how would you use PyTorch to solve your problem? Very practical. You see that's, you have this labels, and you want to use PyTorch to solve your problem. How are you going to solve your problem? Is the question clear? So use PyTorch to learn weights A prime, B prime. So hopefully you can see how if we gave you a homework problem where we said, here are some traces, and the problem literally said, here's traces, here's some file, use PyTorch, generate an estimate A prime, B prime, evaluate how well you do on a held out set of some more traces. You see how that's a well-specified homework? Raise your hand if you understand that as a well, like, we've told you all you need to know to be able to do the problem. Raise your hand if you think that's well specified. Okay, raise your hand if you think it's not. Okay, so let's consider it well specified then. Since most of you did not raise your hand and say it's not. So now, what do you need to do? Let's make this more interactive. What do you need to do this? Like, what's the sort of standard recipe of like neural net style training to get this to work? Yeah, so to set up layers and do backprop, right? Great. Okay, so what do you need to set up layers and do backprop? So first thing, you definitely need a loss, right? So you need a loss. You need a loss layer. Okay? Good. So now let's draw it out. Okay? This is the thing. Let's call A and B the weights. Okay? This is the operation that you're going to be doing. Right? That's the filter. So let's call this entire thing a box with weights W. The weight W equals A prime, B prime. Okay, so this, I'm going to call this the box W. Okay? This box has two inputs. So here's W. Right? You see how this box has two inputs? This and this? Clear, right? So on this side, we're going to say comes in the H, and on this side comes in the X. So now let's just set it up. So we want to learn this for a sequence, and we're going to say, hey, okay, I don't know the hidden state at the start of my sequence, so I'm just going to put in a 0, for example, at the start of my sequence. And then this out comes H hat 1. And the first input goes in, which I think is X 0. Okay? Then I have another, that linear operation thing replicated here. And here is x1, out comes h hat 2. Again, same weights. I guess the way I wrote it is the last thing is x nj minus 1, and out pops h hat nj. Did everyone see that? Like that's the setup layers part 1, right? Is how is the input data being processed? You get all these different h hats. Now you got to put the loss layer in, right? So how does the loss layer work? Well, we're talking about a common filter inspired example. So common filters, we're using mean squared error. So we'll put a squared loss on the problem. And in this case, what is the thing that we want to minimize the squared loss on is on our estimate of the state. So we stick a loss layer up here. So here's a loss h hat 1, and we have a true value in our training data, which is this h hat actual h1, and so on. Is it clear? Is this clear to everybody? Okay, great. Now we've done this, right? And now it's in the form that PyTorch, we know what to do. You pick a learning rate, pick an optimizer, initialize all your W's, and go, right? Now we run, gradient descent, SGD, Atom, whatever, right? Pick learning rate. And you get W. Is that clear to everybody of what we're trying to do here? And how you can do this? This is like shouldn't be like any particular challenge. And notice you have weight sharing, right? We have weight sharing, we have the same weight across, but that's okay. You know how to handle weight sharing. And you know that when you look at the backprop, right, what will happen is this loss, right, will backprop this way. This loss will backprop through here and here. So this backprop will hit, this loss will hit these guys. This lot will hit all three. And this last one will actually hit everybody, right, as a loss. And then you'll get, update the W's from all of them. And you'll apply the sum of all those updates. Any question in the back?
So the question is, so your layers numbers.
Yes, so you think about it from the perspective here of layers, which is really a really great question, right? In terms of the depth of how far backprop has to go, right? So the question is, what's a layer, right? One way we've been thinking about is how far back does backprop have to go? So from that perspective, backprop has to go back through the length of the trajectory, right? But, PyTorch doesn't actually care about it being a layer, right? It just cares that you can do this. So we're actually going to change what layers mean in the context of RNNs in a bit, because we'll get a conflict. two different definitions of layers will conflict with each other, and we'll have to break that conflict. Yeah. So W, the weights that we're learning, are A prime and B prime. So in this box, you simply write this in the line of code that describes this box. And PyTorch will compute derivatives to the weights, which are A prime and B prime. Okay, so you initialize to something. So you look at this, and you should already see that in this picture, everything that you would worry about generally, all your standard worries you can bring to bear, right? And we'll talk about this in a bit. Like, you want to make sure that you have the learning rate to be not so big that, this thing explodes as you learn it, right? You're going to also be worried about, hey, how is this gradient going when it's backpropping through all this, right? Is it going to blow up? Is it going to die, right? So for those who have studied common filters in some detail, as opposed to just doing it, if you initialized at the actual learned, it's a question for you. If you initialize the weights to the actually learned common filter as it should be, okay? If you did that, what do you think would happen to the gradients as you went back? Assuming you're, what do you think would happen to the gradients as you went? Would they explode? Die? It should die? Why do you say that?
Well, because we're already initializing at the value it should be. It should get us good.
Okay, good. So that's a good question, right? So you could say, so remember, you have, so I should say, a very deep and excellent question. So let me repeat the question. The question was, if I initialize to what the actual optimum solution of symbolic calculation of the common filter in steady state would be, then I should be at or very near an optimum. And so you would expect that the gradient that you compute should be 0 at or near an optimum. And while that is true, right, it does bring up an interesting difference. That when you run PyTorch and you compute the gradients and you backprop them through, you actually backprop the gradients on a per sample basis, right? And a sample here is an entire sequence. So, and even in more detail, this particular loss here, right? If you actually had noise, there's actual observation noise here, right? Is going to be not 0. Which means it will actually have a wish for something to be bigger or smaller, right? Which means it'll actually be sending a gradient back, even at the optimum value, right? So what happens in problems where there's no way to actually get your loss to 0, right? For all problems for which there's no way to get your loss to 0, even at optimality, on any individual point, you're going to have gradients. All you're going to say for the optimum is that on average, under the right distribution, all those gradients will cancel out and you'll get 0. Okay? Is that clear to everybody? That's what it means for the gradients to be 0 at optimality across these two things. So there's a difference between these two perspectives. So you could still have exploding or vanishing gradients, right, on every individual sample, while having the overall gradient being 0. Do you see this? It's like a subtle difference, but it's important to keep in mind. So the question I'm asking is, if you have a common filter, and it's for some actual physical system, right? So the actual physical system is not, the actual physical system, this thing is a stable matrix, right? It's not actually blowing up. Then what do you think is going to happen to the gradients as you go back? Okay, people aren't giving an answer, so I would actually recommend, if those, again, this is for people who understand, have some experience. I've actually seen a common filter before. Like, try it out. See what happens. It's good to understand. Yeah, I won't spoil it for you to figure it out yourself. But for all of you, you should see that this is a natural question to ask. Okay? That's the important thing. You need to learn, these are questions that I should ask. I should have this curiosity. I should see what this is. Because it'll help you kind of learn and navigate new things. Okay. So, great. We can do this. That's the easiest case. Let's do a more challenging case, just as an exercise. Suppose you didn't have sequences that had the ground truth state. Harder case. All you have is traces x. All you have is observation traces. Okay? So does everyone understand the question? So the idea is the hidden state is hidden for a reason. You can't see it, right? And so you can't measure it. Are you doomed, right? Or is there anything you can do? So first is the question of what should your estimator actually be? You believe there's a hidden state, right? You have physics reasons, like you built the machine, okay? So it has a hidden state. You know that it's there. You just don't know its parameters that govern it exactly, okay? You know, you might know it approximately. You don't know it exactly. Everything you can think about, you can take the residual of your model from the physics-based model, okay? Like, so effectively think you don't know it. So first thing is, if you have that problem, what do you do? So again, let me first describe it. Suppose that you have these observations that you make, okay? Now, suppose we're right in the classical setup, where you actually know all the true model. What kind of thing could you want to do if all you have is the observations? Right? Yeah. Yeah. You could want to maybe predict the next xt that's going to come out. If you had the common filter, you could make that predictor, right? The next state predictor. Because you could say, I have the current xt. Remember? I did this thing where I had nj minus 1, right? I actually have this h hat. Given the h hat, if I knew the c, again, here, you assume classical, you know it, you can just say, you're never going to be able to predict this v. That's hopeless. But you could at least predict this part. So there is something you can do, right? Next state prediction. Okay, so now I will leave this again as a, because I want to move on to RNN stuff, but it's useful for you to think about how would you then change this? So let's just briefly go through it. It's very briefly. I don't want to go in detail. First thing is, it's very clear that you need to learn more than just A prime and B prime. You have to learn C. Is that clear to everybody? Like classically you're given it, but now so you have to learn the C also. But now you can also basically set up a problem that's like this, where you have losses in terms of the next state prediction. And you see for yourself, like, just like how you do standard system identification, it doesn't bother you the fact that you actually know the next state. You know the next state. You're still going to do next state prediction in classical system ID. Okay? Now, the reason I bring that example up is that you might have asked over here, did we have to actually do all of this if we had access to the true state? Right? You could have said, why am I propagating my h hat through? I could have used my true state and simply learned the next state predictor. But there's a subtle difference between these two. Okay? But in this case, you certainly cannot. There's no way of breaking that. But you can still do next state prediction and have losses. Next observation prediction. Have losses, get gradients, and get everything to work. Okay. So why did I spend all this time talking about things in the linear case? Is because hopefully here, nothing is confusing at all. But it's just all, okay, yeah, all this will work. So now, when we talk about RNNs, okay, so this is exercise. Use C as a parameter, additional parameter. Okay. So nothing should be confusing at all about this linear example. And it tells you we can do learning on this linear example. So now what we want to do is we want to generalize to include nonlinearity. We want a richer expressive model that stays in the same spirit. So what is the generic neural net recipe for taking something linear and generalizing it to include nonlinearity? Anyone? Add activations, yes. So generic recipe, 0. Add activations, right? Generic recipe 1 is a substitution. Replace matrix multiplies with MLPs. Right? Which includes activations which you might do more than one, right? Just generically. So if you do it this way, where it should be instantly clear, right? In terms of like, to carry out this recipe, what you're going to do is you're going to take this block here. Remember, this block is this block. And you're simply going to make these be learnable functions of the previous state. And including, so you don't have to have the plus also, right? You can think of this as a giant matrix multiply, right? This thing is a matrix multiply that looks like this. On a concatenation, right? You see that? That's the, so this can replace with an MLP. Right? And that's the basic idea of an RNN. Standard recipe applied to the case of IR filters. So any questions on that? There's like lots of details now that we're going to talk about in terms of both how you design and compose these things, and details about, hey, do we have to think about the nonlinearities we use and the like. But first, understand the big picture, basic picture. So what that means is you just say H hat. Traditionally now, we used H hat here. We use the hats because we believe there to be a true H. In the RNN community, or in the deep network community, you don't put the hats. You just call them the hidden states. And the reason is that you are agnostic to whether there's actually a true H or not. Right? It's like, well, it would, in a common filter, this would be the estimate of the true hidden state. But I don't even know what's going on in reality, so it's just the hidden state for me. Okay, so RNNs just call this as H. H of t plus 1 is equal to MLP defined by weights W acting on H at time t and whatever input I have. That's my new box. So this weights, again, like, you know, here, traditionally for a common filter, you don't have bias terms because you sit with zero mean, but you know how to adjust it for having bias terms, and you could add bias terms. Not a problem. Here, typically you will have bias terms also. Okay, so we could say we're done, which we kind of are in terms of time, but I want to preview the next two things we want to talk about. But first, any questions on this operation? It should be, I hope it's very, very intuitively clear. So you just, once you understand the linear case, you just like slap on an MLP. So now the design question is, how do I get more complex and interesting behavior from my RNNs? Okay? How do I get more interesting and sophisticated behavior? So if you go back to IR filters, you have two things you can do in an IR filter. And in a way, they're equivalent, they're just philosophically distinct. If you want to do more interesting filtering using an IR filter, you can make a bigger IR filter. Okay? You can add more internal state to your IR filter. And that's a way of making, you know, a more interesting filter. The same way, for a connet, if you want to have a more interesting filter, you could make a bigger convolution. Okay? So that same philosophy can apply here. You could make more interesting things by just making them bigger. What does bigger mean? Bigger means you increase the width inside of the hidden state, and you could add more depth to the MLP inside. Right? All of that could add more expressive power. But coming back to thinking about IR filters and what you saw in connets, you have a different way also of getting more interesting behavior, and that's composition. You can simply compose IR filters with each other, just as you could compose FIR filters with each other. So when you compose FIR filters with each other, you added layers to your connet. So you can do the same thing here and add layers to your RNN. But the instant you do that, we end up with a problem that we now have two different things that we can think about as layers. Adding more filters and going through time. So that's why, like, that's the next thing we'll talk about. Okay, in our treatment of RNNs. So with that, I'll end this lecture. Any questions on the board, you can come up and ask, and then we'll move over to 258. And on Monday, we'll continue and basically finish up RNNs.